All right, we're back. We're on to chapter 27. This is the last chapter we're going to do. It's pretty straightforward stuff. It's how light works. It's really some deep physics going on here, but the equations again, just like in physical optics, where we were looking at index of refraction, index of, and I wish we could do thin film. We're not going to get to thin film, and we're not going to get to relativity, which is just breaking my heart. Um, but that's okay. That's all right. So what I'm going to do is I'm going to do the interference and interference and um, up about 1 or 2 parts of this chapter because we're not going to do all of it. All right. And then on Tuesday when we meet again, I will recap. I will finish chapter 27 and then tell you again what's going to be on the exam when you show up on Wednesday, the next day on Wednesday to take it. You'll learn one extra new thing, and that'll be good. That'll be good. So we're going to do 2 more of these things, and we'll be done. Because I think any more of these, and I know you're probably going crazy, and I really appreciate your being good sports about this. So I can go to Oregon and learn how to learn about the labs that you guys are actually doing. That's one thing I want to do next year. That's one thing I want to do next year is next semester is I want to participate um, in the first semester. I want to go to each 210 lab, not all of them, but like pick one and go to it. Talk to the lab instructor and just go to it and be a lab partner because I think it's important. That's 2 hours in a week. I think it's very important that I learn how to do the freaking lab. All right. So anyway, so I know what's going on, and then I'll do it the next semester with 220. All right. So here we go. When 2 or more light waves pass through a given point, their electric fields combine according to the principle of superposition. Here's what the physical. I used to draw this out, and why I do it's ridiculous why I would do it. In other words, here's constructive interference. Here's wavelength of, notice, 2¼ wavelengths coming in. Here's a wavelength of 3¼ wavelengths coming in. When they combine, boom, they turn into a wavelength. Just add them up of 5½ and constructive interference. Okay. We subtract them. So they've got 3¼ and then so L2 minus L1 gives me 1. So that's constructive interference. And what happens with the waves is they multiply, they go up. Right? It's kind of like if you're skiing out in the Ozarks, taking your life in your own hands. All these people out there with their huge ocean-going type boats cruising through. It's ridiculous. All right, but anyway, and you're bobbing in the water. So this is you out bobbing in the water. Then a boat goes by, and the wake comes. Whoosh, the wake doubles when it hits. And then there's some places where you have destructive interference where it's going to be flat. Ooh, we can't see anything. If this is a light wave, we've got nothing. If this is a light wave here, it's bright. Constructive interference is bright. Destructive interference is dark. All right, and here's the equation for destructive interference. The difference between the 2 wavelengths is n plus 1/2 times the actual wavelength of the light. Now, what we're talking about is we're taking monochromatic light. So what does that mean? Like we're taking red, 760 nanometers, or we're taking violet, 380 nanometers. All right, things like that. And then that's the way we do so that's the difference in the wavelengths now what are we talking about? So we shoot them through, so we shoot these waves, so we shoot these lights. Now look what happens here. You would think that with this single slit, as this light goes through this single slit, that the light we would see would just be a single slit right here. No, it doesn't do that. Why? Because there's diffraction. So light waves do 2 things. Waves do a couple things. They refract, which we learned where they bend in a material where they can bend, that's refraction. They reflect, that's bouncing off a mirror, or that's bouncing off a surface. So they reflect, so they reflect, they refract, and they diffract. This diffraction it's kind of like the Gödel effect. You go through this thing that you go, and you spread out. In other words, they spread out. All right? And because they're so small, since the wavelengths are so small, this slit has to be tiny. I mean tiny. This has got to be a tiny, tiny slit for this to work. Otherwise, it won't work. In other words, it's got to be on an order of magnitude within at least 2 of the wavelength of light. So the wavelength of light is 10 to the negative 7. We need a slit that's width of that slit is only like 10 to the negative 5. Whereas sound waves are big, longitudinal, goopy things, all right? And you can hear my voice, you can hear my cracker voice if we open the back doors of our lecture hall. You can hear my voice down the hall if I was really booming, and around the corner even. Why? Big, goopy waves spreading out all over the place because they're long. They're long, goopy waves. They're going through that opening, which kind of smooshes them together a little bit like this. But the light waves, that opening's way too big. They don't diffract. So you can hear my voice around a corner, but you can't see me around a corner. All right? So here's what we're talking about. Notice, L1 is equal to L2 as they hit the bright fringe. So here's L2 plus an extra little wavelength. So we subtract the wavelengths, and the bright fringe gives us L2 minus L1 is 1 times the wavelength. Because look, if I take L2 minus so that's the first bright fringe. The first dark fringe is L2 plus L2 minus is only a half a wavelength difference. Okay, there's only a half a wavelength difference between the first light fringe and the first dark fringe. This is the first time in 14 years I've ever taught it this way. I was just hiding behind the algebra. I never saw the beauty of this before. I didn't understand the slide. I just kind of go, yeah, okay. No. Notice, the multiple of 1, multiple of a half. Second bright fringe is going to be multiple of 2. In other words, way up here, L2, if it was way up here, minus L1 would be 2 lambda. L3, 3 lambda. Bright fringe 3. And the dark fringes would go 1 half, 3 halves, 5 halves. And down here they go 1 half, 3 halves, 5 halves. And you get a screen that looks like this. Here's their intensity of the lights. These are the intensities. And this is what it looks like. Notice you got this single bright fringe right in the middle, the 0 fringe, which we can also calculate its length. It's the distance between the fringes. And so we've got dark, light. And so the bright fringe of a double slit, that equation is equal to the sine of theta times m over d. Now, the way we do it, here's how we do it. Let me show you, and then we will move on. Then we'll do a new one, because here we go. So we've got interference. We've got interference, all right? So you got the, and I can't draw the pictures very well, so I'll just talk about it. And here's how we normally do it. We normally do d sine theta is equal to m times lambda. This is Young's double slit formula. And he did this back in the 1700s with really crappy equipment and candles. It's amazing. Getting the light to come in, sunlight, things like that. Where d width, of the slit When you're out of width, you're out of slit, or something like that. M is the fringe. 1, 2, 3, 4. Lambda is the wavelength of the light. Okay? This is constructive. Destructive interference looks like this. D sine theta, same thing, width of the slit, angle, this is the angle that it makes, is equal to m plus 1/2 times lambda, where m is equal to 0, 1, 2, 1, 3, 5, 7, and on and on and on. You got 1/2, 3. Wait a minute. Yeah, because 1 would be 3 halves. No, it's 2, 3, 4. Because 4 plus 1/2 gives me 9 halves. Yeah, so that works. So it's 1, 2, 3, 4. On and on and on. Sorry.